In Chapter 3 we looked at quadratic equations, and in Chapter 4 we're going to look more generally at quadratic functions. And we're going to be graphing these functions and then talking about some of the significant features of the functions. So almost every quadratic function that we're going to look at we can refer to as a transformation of y equals x squared. So y equals x squared is our base case. It's our simplest quadratic function. And there's a few things that we can talk about with any quadratic function. And two of those things are domain and range. So since this is a polynomial function, the domain is very easy. The domain is simply all real numbers. And that's true of quadratic functions, it's true of linear functions, and higher degree polynomial functions. The range, as is almost always the case, is a bit more work, and it certainly helps if you have a graph in front of you, because remember, the range is just the set of all y values. So if you look at the graph on the right, the red line represents y equals x squared. Look at all the y values. All the y values are positive. It does get down to 0, and that happens when x is 0, but otherwise, if you think about plugging in different values of x, all you're doing is squaring it. So if you plug in a positive, it becomes positive. If you plug in a negative, it becomes positive. The y values are always going to be positive, and the most compact way of writing the range is just simply y is greater than or equal to 0. Now, one very important point on all quadratic functions is the vertex. The shape of a quadratic function, by the way, has a special name. It's called a parabola. And all quadratic functions are essentially the same. They are all parabolas. Now, we can move the parabolas around to the left and right. We can stretch them out vertically or compress them vertically, which also has the effect of making them look wider or narrower, but really think of it as a vertical compression. And we can flip it upside down. One thing we're not going to do is rotate it onto its side. If we rotate it onto its side, it ceases to become a function. It's still a parabola, but it's not a quadratic function. Alright, if you remember from last year, one of the definitions of a function is that it has to pass a vertical line test, and if you rotated it onto its side, it would fail a vertical line test, so that wouldn't be a function. So the vertex is sort of an obvious point. It's this point right at the bottom. It's the point where there's a reversal. If you're going from left to right, the y values have been going down, 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 and then you get to this turnaround point, the vertex. And then after that, the y values start going up again. So there's our vertex, and the vertex of this quadratic function is the origin, 0, 0. So that's going to be a really important point, because it's the minimum value of this quadratic function. When we refer to the value of the function, we're really talking about the y coordinate. And so this is the smallest y coordinate. And quadratic functions arise in a lot of problems. And sometimes we're looking for the minimum, sometimes we're looking for the maximum. Now, if the quadratic function is upside down, in other words, flipped from the one we have here, then the vertex will represent a maximum. In this case, though, it's a minimum. All right. Let's talk about something else. Quadratic functions are perfectly symmetrical, and there is an axis of symmetry, which is always a vertical line passing through the vertex. And since it's a vertical line, you can write it as x equal to some number. So really all you need to know is the x-coordinate of the vertex, which in this case is 0, and that gives you the axis of symmetry. So the axis of symmetry, I'm going to use a green. The axis of symmetry is this line passing right through the vertex. So we'll call that the axis of symmetry. And it's a very easy thing to find as long as you can find the vertex. Now, let's just take a look at some of the properties of a quadratic function. Notice that if you go 1 unit to the right, you go 1 unit up. And that's not too surprising, because when you square 1, you get 1, and that point is indeed 1, 1. If you go 2 units to the right, you go up 2 squared units. In other words, 4, and that point there is 2, 4. So if you pay attention to this relationship, you can actually pull out some of the numbers in a quadratic function. In other words, if you're looking at a graph, just by analyzing what happens when you go 1 unit to the right of the vertex, that can actually tell you some important things. We're going to get into the meanings of or interpretations of the different coefficients in a quadratic function a little bit later. Let's just go on and take a look at an example from physics. So here is a quadratic function. Y is a function of t this time, where t is time in seconds and y represents the height. And so instead of y, we could have just written this as h. So h is a function of t. And this is the equation for a trajectory of an object that is thrown both up and forward, and well, actually, it doesn't have to be thrown up. Even though it looks like it's moving forward, think of the left or right as a passage of time. So we actually don't know anything about its forward motion. All we know is that it's going up, and the initial velocity is 8 meters per second. That's the second coefficient, the coefficient on t. The last number there, 10, represents the initial height. So in other words, when time is 0, the height is minus 4.9 times 0 plus 8 times 0 plus 10. In other words, the height is 10 at time 0. The minus 4.9 is a special number. It's half of the acceleration due to gravity, which is a constant at sea level on Earth of 9.8 meters per second squared. Now, the derivation of this equation, why you use half of the acceleration and why the initial velocity finds its way into the coefficient on the t, that's a problem that you'll revisit in calculus. And it's a fairly straightforward problem in calculus, but I'll leave the derivation of it until then. One thing I will point out, though, is that the sign on the leading coefficient is negative. And in physics, you define the sign as being a direction. So gravity is a force pulling things down, and we'll define up as positive. So the initial velocity here is 8 meters per second, which means 8 meters per second up, and gravity is pulling in the opposite direction, and so it has a negative sign. All right, so I've got the graph here on the right, and I'm going to show you in a second how to use your calculator, TI-83, to graph this. But let's just analyze a few points on the graph I've got on the right and then see how we can find them on your TI-83. So one obviously very important point is the vertex. So the vertex here is not a nice lattice point. In other words, the coordinates are not integers. It comes out to approximately 0.82. and 13.27. So how do we interpret that? Well, it means that after 0.82 seconds, the object has hit a height of 13.27 meters, and that's its maximum height. So it takes a little less than a second to hit its maximum height, and then the force of gravity overtakes that initial upward velocity and starts pulling it down. And then this is obviously a very important point right down here, because that's the point at which it hits the ground. And so how long does it take for it to hit the ground? Well, this point turns out to be 2.46, 0. So we refer to that as one of the zeros, because that's where the function has a value of 0. In other words, the y-coordinate is 0. And as I said, it's a pretty important point. It tells you that it takes 2.4 seconds, 2.46, almost 2.5 seconds, for the object to hit the ground. Now, this point was, in a way, a very easy point. We already knew that. The y-intercept was 0, 10, and that really just means that you're starting at time 0 at a height of 10. Now, there's another 0 over here, which is negative 0.83. This 0 for our purposes, is meaningless. Really, everything to the left of the y-axis doesn't have any meaning because it doesn't make any sense in our experiment to have negative time. Similarly, we don't really care about anything below the x-axis because we're presuming that it hits the ground. And then, after that, we don't really care. Now, you could set up a different scenario where it's, going into the water, or, the 0, it represents some horizon and it can go below that. But for our purposes, let's just think about the 0, the x-axis as the ground, and so after it hits the ground, it's pretty much game over. So it doesn't really have the same domain and range as the previous one we looked at. The quadratic function, as written, still has a domain of all real numbers, but from the point of view of our problem, we're really only interested in t-values between 0 and 2.46. So it gets a little fussy sometimes when you're asked what the domain of this function is, because it depends whether you want the domain of the quadratic as written or the domain in the context of the problem. Similarly, the range. The range here would be all y values, or all h values if you like, less than the h coordinate of the vertex, which is 13.27. But really, we don't want any negative h values in the context of our problem. So I'm going to leave out domain and range just because they're a little bit finicky for this type of problem. How do we do this on the calculator? So pull up your TI-83 or 84, and I want you to enter the function using y equals. So press y equals. You cannot use t. You have to use x when you're entering the function. So make sure you use the negative sign as opposed to the subtraction sign. It's very, very important when you're entering these functions. The negative sign is on the bottom row to the left of the enter key. So you hit negative and then 4.9 x squared as opposed to t squared. The x is second row from the top and second column, plus 8x plus 10. Now, you could just sort of take a chance and hit graph, but who knows what your window settings are? And your window settings are very crucial here. Your window settings are basically going to allow you to look at a snapshot of this graph. In other words, it'll specify the x values you want to see and the y values you want to see. So a good idea is just to zoom standard. So hit the zoom button right in the middle of the top row below the screen and choose the 6th option, zoom standard. What that does is it sets the x axis, the x window settings to -10 to +10 and -10 to +10 on the y. Now there you can see the quadratic function. But it really doesn't give us everything we want to see, and perhaps gives us a bit too much of some things. For instance, we don't really care about anything to the left or anything to the below the axis, below the x-axis. So let's go to the window settings, and let's change the x-min to -1, and let's change the y-min to -1. So see what the effect of that is. Alright, so now we're primarily looking at quadrant 1, which is much more appropriate for this problem. Positive time values and positive heights. But we still actually don't see the top of this vertex, and so that would be nice. And we really don't care about anything that happens from about 3 seconds on. So let's change the window settings. The x max, x in this case is t, time. Let's make that 3 for 3 seconds. And then the y max, we need to go a little higher than 10. We need to go up to about 15. So now we can see pretty much the same graph that's on the page behind it. Alright, so how do we find some interesting points here? Well, let's find the vertex first. Some books suggest using trace. I would suggest you do not use trace. It will give unpredictable results and it can be very frustrating. However, above the trace button in the top row is an option that says calc. So hit the yellow second function and then hit the trace button to get the calc menu. So this is the calculate menu, and we want to find the maximum. So notice there's no option that says find vertex. So you've got to know ahead of time whether you're looking for a maximum or a minimum. In this case, we're looking for a maximum, and so we choose the 4th option. It'll ask you 3 questions: left bound, right bound, and guess. For the left bound, you must move the the cursor to the left of the vertex and then hit enter. And when it asks you for right bound, you must move the cursor to the right of the vertex. Doesn't matter how far to the right. And hit enter. Now guess would be is if there was more than one possible. In other words, a couple of little peaks. There's never going to be more than one peak with a parabola, and so you don't have to worry about guess. You can just hit enter. And it gives us our maximum with lots of decimal places, 0.8163, etc., a y value of 13.265. So that's pretty much exactly as we had written down before. What if we wanted to find the zero? In other words, how long it takes for it to hit the ground? Well, let's go back to the calc menu, second calc, and there is an option that says 0. So hit the second option, 2 there. So left bound, you've got to be to the left of the 0. It already is, so we can just hit enter. And right bound, you've got to be to the right of the 0. In other words, the cursor has to go below the x-axis. And if you lose sight of the cursor, you can look at the x and the y coordinates to sort of figure out where it is. You can see now that the y coordinate has gone negative. It doesn't have to be that negative, just as long as it is negative is okay. Hit enter and then guess again. If there's more than one place that it's crossing the x-axis in the interval that you specify, you'll need to move the cursor closer to one or the other. But here there's only one in the interval that I've specified, and so I can just hit enter. And it gives us a 0 at 2.46. The y-coordinate obviously is 0. That's exactly what we're looking for when we use the 0 function. And so 2.46 seconds is how long it takes for this object to hit the ground. Okay. Let's just quickly go back to the window settings and I'll point out one or two other things to you. The x SCL is the x scale, and really that just places tick marks on the graph. So if you ignore that completely, it's really not going to change the graph. But if you want your graph to look nice and pretty, you might want to modify that. Now, going from -1 to 3, if we have a scale every 1 unit, that's fine. It's just going to be a few tick marks. But if we were going, let's say, from -100 to +100, and we wanted to put in a tick mark every 1 unit, that'd be 200 tick marks. Well, the screen is not that wide. It's only about 95 pixels wide. And so you really don't want to have that many tick marks, and so you could change the scale to 10, meaning put a tick mark in every 10, or 100, put a tick mark in every 100, whatever you choose to do. Y scale is the same thing, but on the y-axis. And xres, you should always make sure it's 1. This is really just a leftover function from when the calculators were much slower. If you ever get your hands on a TI-83 as opposed to a TI-83 Plus, it'll really be kind of slow, and to speed things up you could change the resolution. Alright, so let's get out of that, and we're going to, in the rest of the chapter, look at all sorts of different ways of interpreting the numbers that appear in a quadratic function and learn different ways of transforming the quadratic function so that we can derive information about the graph. So we're going to be going back and forth between the equation and the coefficients of the equation and the graphs of the equation for this whole chapter.